Hello and welcome back to the channel. Today we will solve this past paper question, and what is important is that this question has 6 marks. And what's interesting is that you don't have to do any math or solve any complicated equations to answer this question. All you need is to understand a simple concept that is called pulse echo technique to answer this question. And that's it. So I was going to start with photoelectric effect, but when I looked at the syllabus, I realized that there are some important concepts which are very easy to understand and which do not involve any math or equations, and still you can expect some like 4, 5, even 6 mark questions from these concepts in AS Physics exam. Let's get started. The first one is understand how the diffraction experiments provide evidence for the wave nature of electrons. So we know diffraction occurs when waves pass through a small gap or around an object and spread out. This is something we see, for example, with water waves and sound waves, and for example, also light. But here's the cool thing. Electrons, which are particles, also show diffraction pattern when passed through tiny gaps like spaces in a crystal lattice. This shows that electrons behave like waves under certain conditions. This is an important result because it connects to the idea that particles can also exhibit wave-like properties, a concept which is central to quantum physics. Now you can expect 3 or 4 mark question from this concept, but in order to get 4 out of 4 marks, you have to include some basic things in your answer. First of all, you need to be familiar with the experimental setup which is used. So we use an electron gun, and this is how the experimental setup looks like. And this is an important thing, that we use thin graphite screen here. We don't use double slit, and we don't use, for example, diffraction grating. We use graphite crystal as our diffraction grating because the electrons are so tiny they will pass straight through the double slit experiment or diffraction grating. So we need very tiny gaps which are provided by the, for example, crystal lattice of graphite crystal. So the electrons will diffract from the spaces between atoms of graphite. Okay, we have evacuated tube, and at the end we don't see, for example, dark and bright lines. We don't see dark and bright spots. What we see is our diffraction rings. So you will see dark and bright rings, concentric rings at the end of the screen. So here I've also written the key points that you must include in your answer. First of all, electron pass through a thin material or crystal, not through a double slit or diffraction grating. Second, diffraction pattern appears as bright and dark rings, not as dark and bright lines or fringes or spots. And the third one, it matches the behavior of waves, providing evidence for wave-particle duality. Next up, we have the Broglie equation, lambda equals h divided by b. Now, what is lambda, what is h, and what is b? So lambda is the wavelength of the wave associated with the particle, h is Planck's constant, and p is momentum of the particle. If you don't remember, momentum is just mass times velocity. The key ideas that you need to remember for exam is, first of all, have basic understanding of this equation, what each term means, and second, you need to understand that this lambda is inversely related to momentum. So lambda is inversely proportional to momentum, which means that for a particle with a smaller momentum, you will get a large wavelength, and also vice versa. If your momentum is large, you will get a smaller wavelength. And if you remember my video on diffraction, I explained that this width of the slit and the wavelength of the incoming wave, if lambda is very large compared to the width of the slit, you will not see any diffraction. And also on the other extreme, if lambda is very small compared to this width of the slit, even then you will not see any diffraction pattern. I also have a small 1 mark question from this concept. So we have to determine the de Broglie wavelength of a person of mass 70 kilograms moving at 2 meters per second. And we also have to comment on our answer. So we will use the de Broglie equation, lambda equals Planck's constant divided by mass times velocity. And if you substitute the numbers, you will get 4.74 times 10 to the negative 36 meters. So you see, this is a very small wavelength, And as a comment on this answer, I will compare this length with the diameter of a nucleus. So nucleus is of the order of 10 to the negative 15 meters. Okay, this is just the width of a nucleus. And you can see that this wavelength and this distance, the difference between these two numbers is about 20 orders of magnitude. So 10 raised to the power of 20. This is how big the difference is. And that's why we can just ignore this wavelength. It cannot be measured. It cannot have any diffraction grating effects. So even if you have a nucleus, you cannot diffract this wavelength of a nucleus, because nucleus is much smaller, right? So you will not see any diffraction pattern for a person moving with this velocity. Next, we have to understand that waves can be transmitted, reflected at an interface between media. To save time, I've already written the answer. So when a wave reaches the boundary between two materials, what happens is, first of all, part of the wave energy is reflected back into the original medium. Second, the remaining energy will be transmitted into the second medium. And the third one that most students forget to mention is absorption. So absorption is also possible. What it means is that if you have a wave passing through some medium, on the other side, because of this absorption, the wave will have a smaller amplitude, right? So some of the energy of the wave was absorbed by this medium, and now the amplitude will be smaller on the other side. Also, the amount of reflection, transmission, and absorption depends on difference in properties of the medium, like density, speed of wave in each medium, etc. And as an example, sound waves reflect more when moving from air into a dense material like wall, and they reflect less when moving between similar materials. So this is also very important. You have to remember that for reflection, if the second medium is more dense, then you will have a higher reflection. And if the second medium is less dense, then you will have more chances of transmission than reflection. Finally, let's talk about pulse echo technique. This technique is used to determine the position of an object using reflected pulses. Here's how it works. A short pulse of radiation, like sound or electromagnetic wave, is sent out. The pulse reflects off an object and returns as an echo. By measuring the time taken for the echo to return, we calculate the distance using a simple equation, which I've written here. Velocity equals distance over time. So we can rearrange this equation for distance. Distance will be equal to velocity times time. But there is a slight difference in the actual equation that we use. The equation that we use has this 2 in the denominator. So we need to divide time by 2 to measure distance. And the reason is that while the pulse goes towards the object and gets reflected back, it covers this distance twice, right? So that's why we need to divide the time taken by 2 to measure distance from one side. Now, this technique has some limitations, and these limitations are really important to understand. For example, you can see we have to understand that the amount of information obtained is limited by the wavelength of the radiation or by the duration of pulses. And in your answer, you have to mention these two limitations. The first one is wavelength. Longer wavelengths reduce precision because they spread out more. And the second one is pulse duration. Shorter pulses give more accurate results because they create clearer echoes. What it means is that if you want to study the details of the object or the shape of the object, you need smaller wavelength. You also need smaller wavelength if you want to go into higher depths. For example, if you want to study some skin disease, you will use longer wavelengths. You don't want the wave to go inside the skin and give you some information about some tissue which is inside the skin. You want the wave to reflect off of the skin, not inside the skin. And if you want to study something, for example, like a tissue, like a tumor, you will use shorter wavelengths. You want the waves to pass through the skin, go inside and reflect off of a tissue and get reflected back, and you will get your information. If, for example, you are studying if for example you want to look at a crack, if for example you want to look at a broken bone inside the body, so you want even shorter wavelengths so that they can pass through the skin. They can also pass through tissues and muscles and reach the bone and get reflected. That's why we use X-rays to look at fractures. So this is very important. the wavelength of the wave that you are using for pulse echo technique depends on what you want to see. If you want to see the outer structure or the outer layer, you use longer wavelength. If you want, for example, the waves to go deep into the material and look at the details, you will use smaller wavelengths. Duration of the pulses has to do with position of the object. So if something is moving, you constantly want updates about its position. So you will use shorter pulses, which means that the time between the pulses will be shorter to get more recent updates about position. And now if you read this question, I'm sure that you can answer this question very easily. So the first question is, a stationary bat emits an ultrasound pulse that is reflected from a moth. The bat detects the reflected pulse 36 milliseconds later. Calculate the distance between the bat and the moth. Speed of sound is given. So we will use our equation. Distance equals speed multiplied by time taken, but don't forget the 2 in the denominator because the distance will be twice. So we need to divide this time by 2. And that's it. You can just substitute the numbers. 36 milliseconds. Don't forget to change these units. You need to convert milliseconds into seconds. And speed is given, so you will get distance. And that's it. You see, 3 marks. The second question is, the bat flies towards the moth. Explain why the bat must change the time between the emitted pulses as the distance between the bat and the moth decreases. So like I just explained here, the pulse duration, if you want to get more recent updates on how the moth is changing its position, you need to change the duration of the pulses. And also, as the bat gets closer and closer to the moth, the distance between them gets smaller and smaller. And that's why the bat needs to change the duration of pulses to, for example, locate the position of the moth. Now, the mistake that students make with these kind of questions is that they think this is just a descriptive question and I can write anything and the examiner will give me 3 or 4 marks. This is completely wrong. These are easy questions, but you have to give very concise, to the point, organized and structured answers. For example, like in this question, you need to include a diagram to explain the experimental setup. So the bottom line is that most students, while solving questions like these, still do not get 4 out of 4 marks or 6 out of 6, for example, for a question like this. And the reason is that they don't include all the key details that the examiner is looking for in their answer. So make sure you include all the keywords, all the key details of a concept in your answer, and you will get full marks.